Okay, so in this video, we're going to talk about the empirical rule, which is something that is very useful when data are normally distributed, or I just wrote it's bell-shaped. Bell-shaped is like the, I don't know, like colloquial way of saying that something follows a normal distribution. We're going to have a more precise definition what that means later on. But for now, we'll show you a picture in a minute what this means. But if it follows a normal distribution or it's the bell-shaped, well, this tells us, the empirical rule is something that tells us what part of the data is within a certain distance from the mean in terms of standard deviations. So approximately 68% of the data is within one standard deviation of the mean. So if you go from the mean, one standard to the left and one to the right, you capture 68% of the data is there if the data follows this normal distribution. And if you go two standard deviations away, two to the left and two to the right, then you capture 95% of the data. And if you move 3, you almost capture all, but not all, 99.7%. Now, this is the picture that we want to keep in our heads. Now, notice carefully that within 3 standard deviations, we don't have we can't guarantee that we have 100% of the data. Okay, we're saying 99.7%. So we're going to use these numbers. Sometimes it's already considered 100, but for technicalities, our textbook and stuff, it's 99.7. Okay, you don't have all the data in 3 standards to the left and 3 to the right. When we talked about the definition for the standard deviation coming from a sample from the population, we said that we rather overestimate the sample standard deviation, and this is kind of a reason why. If you want to say I have 95% of the data here, you rather be guaranteeing that you do have at least that and not less. So you rather go a little bit further down that. It's one way to interpret why we use n-1. So because it's symmetric, this is the shape of a normal curve or of a bell shape of a normal distribution. Because if it's symmetric, if we said that there's 68 here, right? So just because of the symmetry, it's cut off in 34 and 34, right? So that's the same thing. Where is this 13.5 coming from? Again, there's 95 from here to here. There was 68 in the middle, so the difference is 27%. That 27% between 68, right, and 95 is 27% difference. That 27 bit, it's cut in half. So 13.5 is right here, and 30.5 is over there. Yeah, so this is the symmetry is used a lot when you use the normal curve or the normal distribution. And the same reason, the difference between these two values over here is 4.7%, right? So that 4.7 difference is split symmetrically, so in half, 2.35 here and 2.35 over here. Okay, so that's how these 34s and 30.5s get calculated, or that's where they come from. If you know, all the empirical tells you is a 68, 95, and 99.7, but in reality, it's giving you these little cutoffs if you interpret it with symmetry. Okay, let's do, how do we use this? So we're not going to use any technology for these problems. We're just going to kind of this is our first empirical insight into how to use the standard deviation. So here we're saying in the survey by the National Center for Health Statistics, you got the sample mean of height of women between 20 and 29 years old was 64 inches with a sample standard deviation of 2.71. So let's estimate what percent of the women have heights between 64 and 69.42. So these values, this 64 is exactly the mean, right? This 69.42 looks like a random number there. That's a weird. Well, we'll deal with any number later on, but right now, this number is not any number. This number is exactly 2 times the standard deviation above the mean. Yeah, if you multiply 2.71 times 2, you get 5.42. So add that to 64, and it's 69.42. So this is exactly 2 standard deviations above the mean. So if you copy the picture that we had before with the numbers we had, right? So the mean is now 64. 1 standard deviation above that would be 2.71 above that, and another standard deviation above that would land exactly in 69.42. They're asking us between these two values. That's exactly this range, and in that cutoff, we're adding these 34 with a 13.5 that's come from the symmetry that we had before over here, right? So we're adding one of these and one of these, so it's 47.5. Okay, that's how we got this number. So when you have problems to use the empirical rule, it's just about figuring it out, writing your curve. This is like the work is to draw a normal curve, sketch it. It doesn't have to be exact. Write the mean and standard deviation cutoff points, and they're going to ask you where one of these, the areas for one of these cutoffs, what the area is, and just interpret it that way. Let's see one more example. Assume we have a machine that fills 12-ounce potato chip bags. Not all bags weigh exactly 12 ounces. The weight of the chips is normally distributed with a mean of 12.4 ounces and standard deviation of 0.2 ounces. Okay, so this gives me, I'm going to use a empirical rule, so this gives me insight of what shape of what this looks like. So I'm going to sketch a normal curve, a bell-shaped curve, with mean 12.4. So this is 12.4, and the standard deviation is 0.2. So if I move one to the right, is 12.6. One more, it's 12.8. Now, something maybe that I think we should address here is that the scale here is kind of important. Well, we'll have opportunity to say this again more clearly later, but the scale of the normal curve tells us that, see how this is curving up, but here it's curving down? So there's a point in the middle where it should be changes, right, from curving up to curving down. That's called the inflection point. And for those who have taken calculus, and that happens approximately 1 standard deviation away from the mean. Okay, so that gives you an idea when you draw these curves what the scale is when you want to make a that doesn't have to be a perfect curve, but just an approximation of what scale, right? How far are you where this is curving and going slower? So approximately 1 to the right to the mean is that's why I did around this point, 12.6, and over here would be the 12. Follow that rule. This would be the 12.2, right? It's 0.2 to the left. I'm going to go one more just to know 12.0. Okay. So my question here is asking, the first question is asking, if you purchase a bag filled by this dispenser, what is the likelihood? What's the chance that it has less than 12 ounces? So this question is asking for what's the probability that it's in this tail over here, right? The less than 12 ounces is everything on the left of 12. So this is 2 standard deviations, right? This is the mean. So this is 2 standard deviations away from the mean. What I know is that if I do this picture here, this is 1 away, this is 2 away. So there's 95% between here and here, right? And again, I'm going to use a symmetry. There's 95% there, which means there's 5% outside, right? So between both tails, between this that's to the right of the second standard deviation on the right and the one I'm asked for, between both of them, it's 5%. That means that there is 2.5% on this and 2.5% on that, right? Okay, so so I'm asked to the left of 12, so less than 12, so there's 2.5%. I don't know if I should respond here like a probability, like a 0.025. Oh, extra 0, sorry. Like that, or 2.5%. Okay, that would be my answer on that one. The second question says, if you purchase a bag filled by the dispenser, what's the likelihood that it has more than 12 ounces? So that would be to the right, right? It's the same picture, but now I'm asked to the right. So I'm going to have a big mess here, but I'm going to copy most of it and paste it down here. So now I'm asked to find this area, more than 12, right? And I already knew that that was 2.5%, so it's 97.5 on the other side, right? So I don't have to do a lot of work, it's just 97.5%, or 0.975 if you have it as a decimal. Now, the last question says, if you purchase a bag filled by this dispenser, what is the likelihood that it has between 12 and 12.6? Okay, so now I'm adding, I'm going to paste the same picture before I had everything. And now I'm asked between here, so I'm going to fill it with the same color that I had up here. Let's pick a different color with blue. So between 12, so they ask us for this, to 12.4 to 12.6, right? So it's asking between 2 standard deviations to the left of the mean to 1 standard deviation above the mean. That's basically the same picture I had in my last problem. Oh no, it's not. Sorry, it's like it's symmetric. Let me draw it. It's from here. It's from this one, that one, and that one, right? So it's a 68 plus a 13.5, right? So 68 plus 13.5, I think that turns out to be 81.5%, or 0.815. Yes, there's 68% right in the middle, and you're adding a 13.5 from the extra. So these two are between here and here, it's 68. And then there's 13 from here. Okay, so that's how you answer these questions. They are only asking about using the empirical rule to approximate areas. So you use the empirical rule, but also you need to use the symmetry and how much is to the left and to the right in terms of percentages. The total is 100%. And the total, again, you have to remember that this picture doesn't capture 100%. Okay, when you have to, everything to the left on both tails should be 100. You're not seeing 100%. Okay, I'm going to finish now with a more general version of this. It's called Chebychev's theorem. This is not the correct spelling, but this is how some books has it. So the Chebychev's theorem is something very, very important because, well, or very general, because it gives it an insight very similar to the empirical rule. But in the empirical, we had to assume that the data, or had to know that the data we're using follows this normal shape. The strength of Chebychev's theorem is that we don't need anything. Yeah, regardless of the shape of the distribution, you have also some estimations, and it's very, very general. It's very powerful if you think about it. This is saying that even if your distribution has something like this, 2 bumps, or something like that, it doesn't matter. Yeah, it's still going to be true that for k standard deviations away from the mean, at least 1 minus 1 over k squared is within that standard deviation. So what does this mean? Well, for k, sorry, it has to be k more than 1. So for k equals 1, it doesn't make any sense because 1 minus 1 over 1 is 0. It just, okay, that's fine. It's true. 0% of data is there, I guess. But for 2, you say that at least 75% of the data is within 2 standard deviations away from the mean. Okay, I get to 75% because when k is 2, put in this formula, 1 minus 1, 2 squared, becomes 1/4. So it's 3/4. So 75%, or 3/4 of the data, is within 2 standard deviations of the mean, regardless of the shape. Okay, in the empirical rule, that was 95%, right? But this says at least 75, regardless of the shape of the distribution. If you go to 3 standard deviations, it's 1 minus 1/9, so 8/9 of the data, which is 88.9%, would be captured between 3 standard deviations to the left and 3 to the right of the mean. And the empirical rule, again, if you have a normal distribution, that's 99.7. But for any shape, Chebychev's theorem says it's at least 88.9%. So this is a very powerful theorem, and in some applications, you might need to use this one. Okay, we're done for this topic.